The history of artificial intelligence, AI, began in antiquity with myths, stories, and rumors of artificial beings endowed with intelligence by master craftsmen. The study of logic and formal reasoning from antiquity to the present led to the development of the programmable digital computer in the 1940s, a machine predicated on abstract mathematical reasoning. This device and the ideas behind it inspired scientists to begin discussing the possibility of building an electronic brain. The field of AI research was founded at a workshop held on the campus of Dartmouth College in 1956. At the workshop, the first AI program, Logic Theorist, was presented by future Turing awardee Alan Newell and future Nobel laureate Herbert A. Simon, with help from J.C. Shaw. Attendees of the workshop became the leaders of AI research for decades. Many of them predicted that machines as intelligent as humans would exist within a generation. The U.S. government provided millions of dollars with the hope of making this vision come true. It became apparent that researchers had underestimated the complexity of this objective. In 1974, criticism from James Lighthill and pressure from the U.S. Congress led the U.S. and British governments to stop funding undirected research into artificial intelligence. 7 years later, a visionary initiative by the Japanese government and the success of expert systems reinvigorated investment in AI. And by the late 1980s, the industry had grown into a billion-dollar enterprise. However, investors' enthusiasm waned in the 1990s, and the field was criticized in the press and avoided by industry, a period known as an AI winter. Nevertheless, research and funding continued to grow under other names. In the early 2000s, machine learning was applied to a wide range of problems in academia and industry. The success was attributable to the availability of powerful computer hardware, the accumulation of expansive datasets, and the application of rigorous mathematical methods. Soon after, deep learning proved to be a breakthrough technology, eclipsing all other methods. The transformer architecture, introduced in 2017, and was utilized to produce generative AI applications, among other implementation. Investment in AI boomed in the 2020s. The recent AI boom, initiated by the development of transformer architecture, led to the rapid scaling and public releases of large language models, LLMs, like ChatGPT. Mechanical men and artificial beings appear in Greek myths, such as the golden robots of Hephaestus, the bronze giant Talos, and Pygmalion's Galatea. In the Middle Ages, there were rumors of secret mystical or alchemical means of placing mind into matter, such as Jabir ibn Hayyan's Takwin, Paracelsus' homunculus, Rabbi Judah Lo's golem, and Roger Bacon's brazen head. By the 19th century, ideas about artificial men and thinking machines became a popular theme in fiction. Notable works include Mary Shelley's Frankenstein, 1818, Johann Wolfgang von Goethe's Faust, Part 2, 1832, and Karel Čapek's RUR. Rossum's Universal Robots, 1921. Stories of these creatures and their fates consider many of the same hopes, fears, and ethical concerns that are presented by modern artificial intelligence. Issues relevant to AI were also discussed in speculative essays such as Samuel Butler's Darwin Among the Machines, 1863. Realistic humanoid automata were built by craftsmen from many civilizations, including Yen Shur, hero of Alexandria, Al-Jazari, Harun al-Rashid, Jacques de Vaucanson, Leonardo Torres y Quevedo, Pierre Jacques Draz, and Wolfgang von Kempelen. The oldest known automata were sacred statues of ancient Egypt and Greece. The faithful believed that craftsmen had imbued these figures with very real minds, capable of wisdom and emotion. Hermes Trismegistus wrote that by discovering the true nature of the gods, man has been able to reproduce it. See also, Reason section, Philosophical History. Artificial intelligence is based on the assumption that the process of human thought can be mechanized. Chinese, Indian, and Greek philosophers developed structured methods of formal reasoning by the first millennium BCE. Formal logic was invented and improved by Greek, Islamic, and European philosophers, such as Aristotle, Euclid, Al-Khwarizmi, Duns Scotus, and René Descartes. Spanish philosopher Ramon Llull, 1232 to 1315, developed several logical machines devoted to the production of knowledge by logical means. Llull described his machines as mechanical entities that could combine basic and undeniable truths by simple logical operations, produced by the machine by mechanical meanings, in such ways as to produce all the possible knowledge. Llull's work had a great influence on Gottfried Leibniz, who redeveloped his ideas. In the 17th century, Leibniz, Thomas Hobbes, and René Descartes explored the possibility that all rational thought could be made as systematic as algebra or geometry. Hobbes wrote in Leviathan, "For reason is nothing but reckoning, that is, adding and subtracting." Leibniz described a universal language of reasoning, the characteristica universalis, which would reduce argumentation to calculation, so that there would be no more need of disputation between two philosophers than between two accountants. For it would suffice to take their pencils in hand, down to their slates, and to say to each other, with a friend as witness, "If they liked, let us calculate." Boole's The Laws of Thought, 1854, and Freya's Begriffsschrift, 1879, defined the modern form of symbolic mathematical logic. The earliest research into thinking machines was inspired by a confluence of ideas that became prevalent in the late 1930s, 1940s, and early 1950s. Recent research in neurology had shown that the brain was an electrical network of neurons that fired in all-or-nothing pulses. Norbert Wiener's cybernetics described control and stability in electrical networks. Claude Shannon's information theory described digital signals, i.e., all-or-nothing signals. Alan Turing's theory of computation showed that any form of computation could be described digitally. The close relationship between these ideas suggested that it might be possible to construct an electronic brain. In the 1940s and 50s, a handful of scientists from a variety of fields, mathematics, psychology, engineering, economics, and political science, explored several research directions that would be vital to later AI research. Alan Turing was among the first people to seriously investigate the theoretical possibility of machine intelligence. The field of artificial intelligence research was founded as an academic discipline in 1956. In 1950, Turing published a landmark paper, Computing, Machinery, and Intelligence, in which he speculated about the possibility of creating machines that think. In the paper, he noted that thinking is difficult to define and devised his famous Turing test. If a machine could carry on a conversation over a teleprinter that was indistinguishable from a conversation with a human being, then it was reasonable to say that the machine was thinking. This simplified version of the problem allowed Turing to argue convincingly that a thinking machine was at least plausible, and the paper answered all the most common objections to the proposition. The Turing test was the first serious proposal in the philosophy of artificial intelligence. Artificial neural networks. Walter Pitts and Warren McCulloch analyzed networks of idealized artificial neurons and showed how they might perform simple logical functions in 1943. They were the first to describe what later researchers would call a neural network. The paper was influenced by Turing's paper on computable numbers from 1936, using similar two-state Boolean neurons, but was the first to apply it to neuronal function. One of the students inspired by Pitts and McCulloch was Marvin Minsky, who was a 24-year-old graduate student at the time. In 1951, Minsky and Dean Edmonds built the first neural net machine, the SNARK. Minsky would later become one of the most important leaders and innovators in artificial intelligence. Cybernetic robots. Experimental robots, such as William Gray Walter's Turtles and the Johns Hopkins Beast, were built in the 1950s. These machines did not use computers, digital electronics, or symbolic reasoning. They were controlled entirely by analog circuitry. Game AI. In 1951, using the Ferranti Mark I machine of the University of Manchester, Christopher Strachey wrote a checkers program and Dietrich Prinz wrote one for chess. Arthur Samuel's checkers program, the subject of his 1959 paper, Some Studies in Machine Learning Using the Game of Checkers, eventually achieved sufficient skill to challenge a respectable amateur. Samuel's program was among the first uses of what would later be called machine learning. Game AI would continue to be used as a measure of progress in AI throughout its history. The programs developed in the years after the Dartmouth workshop were, to most people, simply astonishing. Computers were solving algebra word problems, proving theorems in geometry, and learning to speak English. Few at the time would have believed that such intelligent behavior by machines was possible at all. Researchers expressed an intense optimism in private and in print, predicting that a fully intelligent machine would be built in less than 20 years. Government agencies like the Defense Advanced Research Projects Agency, DARPA, then known as ARPA, poured money into the field. Artificial intelligence laboratories were set up at many British and U.S. universities in the latter 1950s and early 1960s. 49. Stanislav Lem's philosophical essay on intellectronics appeared in Lem's Summa Technologiae in 1964. Approaches. There were many successful programs and new directions in the late 50s and 1960s. Some of the most influential included reasoning, planning, and problem-solving as search. Many early AI programs used the same basic algorithm to achieve some goal, like winning a game or proving a theorem. They proceeded step by step toward it by making a move or a deduction, as if searching through a maze, backtracking whenever they reached a dead end. The principal difficulty was that, for many problems, the number of possible paths through the maze was astronomical, a situation known as a combinatorial explosion. Researchers would reduce the search space by using heuristics that would eliminate paths that were unlikely to lead to a solution. Newell and Simon tried to capture a general version of this algorithm in a program called the General Problem Solver. Other searching programs accomplished impressive results, like solving problems in geometry and algebra, such as Herbert Gelernter's Geometry Theorem Prover, 1958, and Symbolic Automatic Integrator, SAINT, written by Minsky's student James Slagle in 1961. Other programs searched through goals and subgoals to plan actions, like the STRIPS system developed at Stanford to control the behavior of the robot Shaky. An important goal of AI research is to allow computers to communicate in natural languages like English. An early success was Daniel Bobro's program Student, which could solve high school algebra word problems. A semantic net represents concepts, e.g., house, door, as nodes, and relations among concepts as links between the nodes, e.g. as a. Ross Quillian wrote the first AI program to use a semantic net, and the most successful and controversial version was Roger Shank's conceptual dependency theory. Joseph Weizenbaum's ELIZA could carry out conversations that were so realistic that users occasionally were fooled into thinking they were communicating with a human being and not with a computer program. See ELIZA effect. But in fact, ELIZA simply gave a canned response or repeated back what was said to it, rephrasing its response with a few grammar rules. ELIZA was the first chatbot. Microworlds. In the late 60s, Marvin Minsky and Seymour Papert of the MIT AI Laboratory proposed that AI research should focus on artificially simple situations known as microworlds. They pointed out that in successful sciences like physics, basic principles were often best understood using simplified models like frictionless planes or perfectly rigid bodies. Much of the research focused on a blocks world, which consists of colored blocks of various shapes and sizes arrayed on a flat surface. This paradigm led to innovative work in machine vision by Gerald Sussman, Adolfo Guzman, David Waltz, who invented constraint propagation, and especially Patrick Winston. At the same time, Minsky and Papert built a robot arm that could stack blocks, bringing the blocks world to life. In the 1980s, a form of AI program called expert systems was adopted by corporations around the world, and knowledge became the focus of mainstream AI research. Governments provided substantial funding, such as Japan's fifth-generation computer project and the U.S. Strategic Computing Initiative. Overall, the AI industry boomed from a few $1 million in 1980 to billions of dollars in 1988. Expert systems become widely used. An expert system is a program that answers questions or solves problems about a specific domain of knowledge, using logical rules that are derived from the knowledge of experts. The earliest examples were developed by Edward Feigenbaum and his students. Dendril, begun in 1965, identified compounds from spectrometer readings. Mycin, developed in 1972, diagnosed infectious blood diseases. They demonstrated the feasibility of the approach. Expert systems restricted themselves to a small domain of specific knowledge, thus avoiding the common sense knowledge problem. And they're simple. Design made it relatively easy for programs to be built and then modified once they were in place. All in all, the programs proved to be useful, something that AI had not been able to achieve up to this point. In 1980, an expert system called R1 was completed at CMU for the Digital Equipment Corporation. It was an enormous success. It was saving the company $40 million annually by 1986. Corporations around the world began to develop and deploy expert systems, and by 1985, they were spending over $1 billion on AI, most of it in in-house AI departments. An industry grew up to support them, including hardware companies like Symbolics and Lisp Machines, and software companies such as IntelliCorp and ION. Government funding increases. In 1981, the Japanese Ministry of International Trade and Industry set aside $850 million for the fifth-generation computer project. Their objectives were to write programs and build machines that could carry on conversations, translate languages, interpret pictures, and reason like human beings, much to the chagrin of Scruffies. They initially chose Prolog as the primary computer language for the project. Other countries responded with new programs of their own. The UK began the £350 million ALVI project. A consortium of American companies formed the Microelectronics and Computer Technology Corporation, or MCC, to fund large-scale projects in AI and information technology. DARPA responded as well, founding the Strategic Computing Initiative and tripling its investment in AI between 1984 and 1988. Knowledge revolution. The power of expert systems came from the expert knowledge they contained. They were part of a new direction in AI research that had been gaining ground throughout the 70s. AI researchers were beginning to suspect, reluctantly, for it violated the scientific canon of parsimony, that intelligence might very well be based on the ability to use large amounts of diverse knowledge in different ways. Writes Pamela McCorduck. Her great lesson from the 1970s was that intelligent behavior depended very much on dealing with knowledge, sometimes quite detailed knowledge, of a domain where a given task lay. Knowledge-based systems and knowledge engineering became a major focus of AI research in the 1980s. It was hoped that vast databases would solve the common-sense knowledge problem and provide the support that common-sense reasoning required. In the 1980s, some researchers attempted to attack the common-sense knowledge problem directly by creating a massive database that would contain all the mundane facts that the average person knows.